In the automotive world, vibration is all around us. It might originate from a misfiring engine or a tyre that's out of round. It might even be normal operation for the vehicle in question. Abnormal vibration occurs due to an imbalance of a rotating or reciprocating component, and each is unique in the sound and feel produced. While some vibration is to be expected during normal vehicle operation, there are limits to what a customer will tolerate. It's our job as automotive professionals to define what is acceptable and what isn't. In this module, we'll take a look at what vibration is, how it occurs, and some relevant information around diagnosing vibration concerns. To understand the concept of vibration and how it can originate from imbalance, let's take a look at a simple cooling fan. A rotating fan with an equal number of blades of equal mass and size positioned around a central hub should be reasonably balanced, both static and dynamically. If we remove one blade, the fan would vibrate when rotating. While not overly noticeable at low RPMs, it will be quite violent at speed. This is due to imbalance of the fan. By definition, vibration is the movement of a component from its static position or equilibrium. In the case of the fan, the imbalance is caused by the missing blade. With all blades intact, the fan rotates on its axis evenly. Each blade passes a given point in time where there is an equal and opposite force exerted, so the unit is kept in equilibrium. With one of the blades missing, the fan will move off its axis and fall out of equilibrium and begin to vibrate. Each movement away from and back to its axis is called a cycle. Frequency is a term we use to describe how often an event occurs during a fixed period of time. In terms of vibration, the event is called a cycle, and the period of time is 1 second. Therefore, frequency is measured in cycles per second. In this example, we can see that there are 3 cycles or events occurring over the period of 1 second. We refer to this as 3 Hz. We can say that the frequency of the vibration is the number of times that the fan moves away from and back to its axis in 1 second. Amplitude, when related to automotive vibration, is simply a measure of the magnitude of the disturbance. A severe disturbance will generally have a high amplitude, whereas a minor disturbance would have a low one. We see this in a vehicle wheel that has a large imbalance. The amplitude will increase with a rotational speed increase. At around 15 km an hour, the imbalance would not be noticeable. But at 100 km an hour, due to the increase in amplitude, the vibration felt at the steering wheel would be unacceptable. All objects have natural frequencies. We might not be able to tell by looking or touching them, but they still exist. A natural or resonant frequency is one at which an object tends to vibrate without external force or excitement. The lower a component's natural frequency, the less likely we are to feel vibration. If we observe a typical front suspension system, it resonates with a frequency range of between 15 and 20 Hz, regardless of vehicle speed or suspension travel. If we introduce an imbalanced wheel to the suspension system, we can see that as the road speed increases, the disturbance created by the imbalance also increases in frequency. Eventually, the frequency of the unbalanced wheel will intersect with the natural frequency of the suspension, causing a vibration that travels through the steering and suspension components to be felt by the driver. Vibration can be due to centrifugal action through rotation, like an imbalanced tyre. Or it can be linear in origin, like a flat spot on a tyre. An imbalanced and rotating wheel will cause a centrifugal force that alternately lifts the wheel up and down and side to side with every revolution of the wheel. As the vehicle speed increases, we can feel the disturbing force caused by the imbalance through the steering wheel as shimmy, then through the seat and floor as vibration. Where centrifugal vibrations cause a force to be exerted in all directions, linear vibrations cause the force to only be exerted in two directions. A tyre with a high or flat spot will cause a linear vibration. As the tyre turns and rolls over the imperfection, the wheel hub is alternately raised and lowered. Linear vibrations can be subclassified as runout or radial force variation. This force will be felt through the same components as the centrifugal vibration, but it won't produce the shimmy at the steering wheel. When production vehicles are designed, allowances must be made for the natural resonance of the materials used in their construction. One way to overcome or change a component's resonance is by constructing it out of a fairly dense or a high mass substance. The greater its mass, the lower its natural frequency. The stiffness or rigidity of this mass also has an effect on its resonant frequency. Vehicle components with little flex, such as exhaust systems, chassis rails and body panels, have higher resonant frequencies than softer ones, like rubber mounts and suspension bushes. Damping is the ability of a material to dissipate or absorb vibration energy. And this is why engine and suspension mounts are made from a soft, dense material that is able to absorb and dissipate vibration. Vibrations tend to transmit themselves through the body or chassis of a vehicle. The cause of the vibration may originate from the rear of the car, but the customer will tell you it's coming from the seat, floor or steering. There are three key identifiers that need to be taken into account when diagnosing vibration concerns: the source, or where the vibration originates from, the transfer path that the vibration takes through the vehicle, and the responder, which is the component that the customer feels the vibration through. Eliminating any one of these elements will usually correct the condition, although this is not always practical or economical. We must decide from the information gathered during the diagnosis which element makes the most sense for the repair.